I have a habit of always changing my titles, at least a small amount. And so maybe a more accurate title for this would be temporal multiplexing, quantum temporal multiplexing, and it's all about time, but also a lot about loss. Or I could go to my original, more generic title, something about photons. Okay, so this is sort of the three things, three main areas I want to discuss. One is single photon sources and quantum memories, and then a wish list of technologies I wish I had, and maybe someone out there will help create such a thing. Okay, so let's start with single photons. So a lot of this work all the work I'm going to be reporting has been from people in my group, and in particular, I just want to highlight three. So Fumihiro Kaneda was a postdoc in my group who left a couple years ago, but he certainly started a lot of this work. And then that's been taken up by Colin Lualdi. And also some of the memory work I'll be talking about is now being worked on by Michelle Victora. So single photon sources. Now you basically have three, so single photons are very important resources for a lot of quantum communication protocols. You can use them to build up entangled sources. You can use them for metrology, quantum repeater networks, all kinds of interesting and relevant quantum information applications. What you'd really like is a box where when you hit a button, exactly one photon comes out, and in a well-defined direction at a well-defined time. And we don't really have such a box like that on the planet at the moment. So I'll describe what we do have. So there's sort of three main approaches you could follow. By far the easiest is just to take an attenuated coherent source, like an attenuated laser pointer. And that has the huge advantage that it's very easy. And in fact, it is sufficient for some quantum protocols like quantum key distribution. There are protocols that can where that's a sufficient amount of quantumness, if you will. But basically, that's going to be insufficient for most other applications. And one of the main reasons is that the statistics of the photons, in that case, are Poissonian. So I've shown here just the probability of getting different photon numbers for different driving the source at a different intensity. So for example, we could imagine being in this outer curve where we're driving pretty hard. So we have here a pretty high probability of producing a single photon, also pretty high actually, let me do my, nope, not that. Let's do laser pointer. Okay, so I think you can see that. So we have a pretty high probability of getting one photon, but there's also a very high probability of getting 2 and 3 and more. So, okay, I can suppress those higher photon numbers by driving more weakly so that I don't have, for example, if I take this inner curve, I have very small probability of getting 2 or more photons, but I also have a small probability of getting 1. So that's going to not be very useful. And just the fact that if I have a coherent state, the overall statistics means it's really going to be not appropriate for some experiments that I want to do. Okay, so another option is we could have a single emitter, like a single atom or a single quantum dot. And in that case, that's good, because if I only have one emitter, then when I excite it, I'll presumably only get out one photon. Let's see, I have this G2 listed here, so let me just talk a minute about that, because that's going to come up often as a way of characterizing a single photon source. So that's the second order correlation function defined in this sort of complicated way here. It basically tells you in the simplest form, whether or not you have more than one photon. So if you have any kind of a classical source, it turns out that the G2 function, and you're basically looking maybe at 2 different times at the same spatial mode, or maybe you send photons onto a beam splitter and you look at the 2 outputs, and that's how you can measure the G2. And basically, if you have a single photon, then only one of those 2 outputs should get the photon. And so what I'm plotting here, showing here is a plot of the G2 versus, for example, the time between when you might get multiple photons. And if I have a coherent state like a laser, then it turns out, because the photons are all independent from each other, the G2 is always equal to 1. And in fact, you need to have a G2 less than 1 to have non-classical light. And what's shown in red here is if you had, for example, a single atom and you're driving it with a laser beam, if you look at a short enough time after you've hit the atom, you'll only produce one photon. You won't produce two photons because it takes time to re-excite the atom and then for it to re-emit. So at very short times, you get a G2 going to 0, and that's exactly what you want. I've shown in this formula over here, if you had a state that has n photons in it, what the G2 would be, and when n is equal to 1, G2 goes to 0. So that's the goal that we want. Okay, so if I have, go ahead.
Oh, this is Jim. Can I interrupt you with a question? Is that okay?
Yeah, please.
If you think about all the ways of getting light out of atoms, I mean, there's the laser where you've got stimulated emission, and you've got this thing you just are talking about right now, which is sort of spontaneous emission. Do all stimulated processes lead to some kind of, lead to a Glauber state, really? That's what I'm wondering. I think that's the way of saying my question.
What are you defining as a Glauber state, a photon number state?
No, it's this thing that's in the textbook that I studied back in the 1970s, which was, I think, just also called a coherent state. You know, it's this.
Yeah, yeah.
Does it have to be one or the other?
No, you can have complicated things in between, and in fact, this thing that I'm showing right here could be a stimulated process. It's not necessarily a spontaneous process. So you can excite something to the excited state and then resonantly drive it back down. But then you have all this background light, so that's probably going to be a problem.
Yeah. Okay. All right. Well, that was my question. Maybe I'll think about it more.
There's another question. Maris, are you talking?
Yeah, it looks like G2. I have the chat window open.
Oh, okay.
So like G2 is related to the out of order correlation. Well, you're looking at two different times and potentially two different times and two different spatial. If you were to look at it in terms of just like raising and annihilation operators at the same time in the same mode, it would look like A dagger, AA. At least I think I got that, unless I got those backwards, but I think that's right. Okay, so let's go back to our single emitters here. So they have, in principle, a very good G2. They, in principle, can be deterministic. The main difficulty with them is that, in general, they tend to emit the photon in all directions, so it can be difficult to catch that photon. You can try and put cavities on and improve that, and I'll talk about that in just a second. Oftentimes, they need to be cryogenically cooled, like with quantum dots, for example. And in some cases, getting identical emitters can be a challenge, again, in the quantum dot case. You make two of them, they don't necessarily produce photons of the same wavelength. Okay, and then the final option, which we'll spend most of our time talking about, is having a pair source where I make a pair of photons, I detect one of them, and that heralds the presence of the other one. And those have some great advantages in terms of mode matching and having a high efficiency of knowing where your photons are. Usually they run at room temperature, but they have an issue that they can be probabilistic and they can create multiple pairs. And that's what we'll spend most of the time talking about. So just to give a sense of what we're competing against. So here's a fairly recent paper using a quantum dot as a single photon emitter. There's a quantum dot that's embedded in a cavity, and it's excited by shining light on it resonantly and then letting it decay through this cavity. And if you look at the paper where it says high extraction efficiency and 66% and very good purity and indistinguishability, we'll come back to those quantities in a minute. So it sort of seems like it's working really well. But if you look at the actual efficiency in their paper, so how many photons they're actually collecting into their detection system, divided by how often they're hitting their source, they're running it at, driving it at 81 megahertz, they only have an efficiency of something like 5%. And even if you divide out the fact that their detectors are not very efficient, they're only putting their photons into a fiber something like 15% of the time. It turns out because of the way that they're driving it, in fact, they have an automatic 50% loss, although there's been recent work where they've been able to fix that. But nevertheless, these sort of sources have traditionally been pretty limited at how well they can actually couple photons into fibers. Nevertheless, this has been the workhorse, for example, of some experiments, for example, out of China. So this is out of John Ray Pan's group. So on the left-hand side, they have one of these quantum dot sources, and they're driving it repeatedly. So they're making a whole string of photons. They are demultiplexing them. So they're taking that string and converting, say, 14 photons sequentially into 14 photons coming simultaneously into these different spatial modes. And this is an experiment trying to do boson sampling. And on the right-hand side, this is just showing as they change the driving field that's driving their quantum dot, they can either have nothing coming out of it or have a high probability of things coming out of it. And then if they overdrive it, they basically start, it's like a Rabi oscillation. So they drive it back to the ground state. Okay, so they've been able to get this working, but in their case, because their efficiency here was only about roughly 20% or 25%, the rate of their 14 photon events, where they actually detect 14 photons at the end, is only something like 6 times an hour. So that's actually not going to be very useful for any kind of application. As an experimentalist, I'll also point out sort of 2 other things that are not so great. So in their demultiplexer, they have a total of 19 Pockle cells, and they have 60 of these superconducting nanowire detectors, and each of these Pockle cell and nanowire detectors costs about $15,000. So they have, over $1 million worth of hardware to do this one experiment. So that's maybe not the best, maybe not the best strategy. Okay. I'm just going to show one more thing. This is from another group in Paris that makes these sources where they have the quantum dot, which is embedded in this micropillar cavity. And the main reason I wanted to put this is that oftentimes quantum dots previously have been, people have been pretty pessimistic because it's hard to get 2 of them to emit photons that look identical. But in fact, they've been doing a lot of work on that over the past decade and have been able to create, for example, 15 different quantum dots, which all are producing photons that are pretty indistinguishable from each other. And so that's actually looking pretty well. But nevertheless, they still have not great efficiency coupling into single mode fiber. Okay, so instead, we want to focus on using a 2-photon source. So we can either use spontaneous parametric downconversion or 4-wave mixing. I'll talk about the former. That's where we take 1 high energy photon and it splits into 2 daughter photons. In 4-wave mixing, you take 2 pump photons and they are converted into 2 daughter photons. And the thing is that because I'm creating 1 pump photon into 2 daughter photons, as long as I detect 1 of those daughter photons, I know that there's another one. It's never possible to have only 1, for example, to have a heralding photon and not have its twin photon, because that would not satisfy energy conservation. And moreover, the momentum correlations can be quite strong between these, so that if I detect 1 photon into a single mode fiber, I can definitely project the other photon being into a single mode fiber. But there is a pretty big downside of these, which is that the process is governed by thermal statistics. And so that means that the probability of producing K pairs in this case is governed by this formula, where mu is the average number of pairs per pulse that we'd be creating. So of course, in a thermal process, the most likely state is the one that has the lowest energy. So most likely you won't make any pairs, and then next highest likely would be 1 pair, then 2 pair, then 3 pairs. So if we don't drive very hard, most of the time we're not making any pairs. So that means the single pair probability is, goes to 0. We could drive harder, and then that single pair probability will increase, but eventually it'll start to decrease, because now what's happening is we're also producing 2 pairs and 3 pairs and higher numbers of pairs. So the best that you can do with this sort of a source is a 25% probability of producing exactly 1 pair. Okay, so that seems like that's a pretty bad limitation. And now we want to discuss how we can circumvent that limitation by using multiplexing techniques. But first, let me just say that this technique has also been used in another boson sampling experiment, also from John Ray Pan's group in China. And this is an experiment where they're trying to do this with 12 photons. And the way that they make their 12 photons is they have 6 of these downconversion sources. And they just hope that when they drive these, that they happen to produce one pair in each of these sources, in each of these crystals. Now, that's not very likely. First of all, it's not necessarily likely to produce 6 pairs regardless, but it turns out that you're equally likely, for example, to produce one pair in each of the crystals as you are to produce one pair in each of the 4 crystals, 2 pairs in the 5th one, and nothing in the 6th one, and all other possible permutations. And so although they were able to make this is the world's largest photon entangled state, a 12-photon entangled state, nevertheless, their success rate of getting this was only about once per hour. So again, despite what they may say in their papers about this being a totally enabling technology, in fact, it doesn't really enable anything, but it does enable, a purchase of a lot of equipment, I suppose, and having to wait a very long time in order to get statistics in order to measure these states. Okay, so the solution is that we can instead incorporate multiplexing, and that's going to allow us to do quite a bit better. Okay, so here's just a single source with our trigger detector. And here's the simplest way you might think about doing multiplexing, which is instead of having one source, let's say I have 20 sources, and I'm going to drive them all simultaneously, and I'm going to see which source happen to produce a photon pair. And I know that because I have this trigger detector. So if this detector goes click, I know that this source produced a pair. It might be that some other sources produced a pair, but I didn't detect it because my detector is not perfectly efficient. That's fine. That doesn't hurt me particularly badly, because it's only when I get a click at this detector that I know that this source has produced a pair. And then I know that there's this other photon there, and I can route that through some sort of a switching circuit into a single output. Okay, so that does require obviously many crystals, also many detectors, and also a very low loss photon switchyard. And that in fact is not that easy to get at the moment. So that's maybe not the best approach. So instead we can do a temporal multiplexing approach. So in this case, this is if I just drive one of these crystals with a bunch of pulses, and I ask where they come out, and it's going to be random where they come out. So if I look at any given time bin, I'll have a low probability of having a photon pair. In principle, I could drive a lot harder, and so that I could increase the probability of getting a photon pair, but then many of my bins would have 2 photon pairs in them, and I don't want that. So I really want to have a case where I'm only having single bins. But what I can think about doing is thinking about these, for example, in this case, 4 bins as one multiplexing cycle. And because I'm looking at a number of bins here, the likelihood that I produce a pair in some larger number of bins, of course, is going to be higher. And as I go to more and more bins, then that probability is going to eventually saturate to 1 to have a probability of 1 that at least one of those bins will have a pair in it. Okay, and then I need to have some way of switching them, of switching the photons so that it always goes into the same time bin. So let me just show how that might work with this little movie here. Okay, so I'm driving my crystal here. In that case, I happen to produce a pair, but I didn't detect it. In this case, I didn't produce a pair. Okay, another pump pulse coming in. In this case, oh, I happen to have produced 2 pairs, and both of my detectors went click. So I know I didn't have a single photon, so I don't bother trying to store it. That was another good photon, single photon, but I didn't detect it. No pairs. Okay, my intuition tells me this next event might be a good one, where I'm going to produce 1 pair, and I'm going to detect it at one of these 2 detectors, and then I'm going to store the other photon in a storage cavity. And I'll talk a little later about how we're going to do that. And the goal is that when my clock gets to the top, I'm going to release it. So I'll be able to release it at a predetermined time. But note there's a problem that this photon is getting dimmer and dimmer because there's loss. And so what I'd really like to do is switch it for a fresh photon if I could, a photon that doesn't have to stay in the cavity as long. And in that case, then I'll have a higher probability of being able to emit a photon at the end. So that's the basic idea. I want to detect when my photons are coming by using these heralding detectors. And once I have that, I'll know how long I need to store the twin photon for so that it's always released at the same time. Okay, so we have created such a source in my laboratory. So we have a downconversion source, we're pumping it. In this case, we are producing photons at 777 nanometers and 1590 nanometers. And the trigger or the heralding detector is the 777 one. And then I take the other photon and I put it into the storage system. The length of this loop, sorry, let me go back to my laser pointer here. The length of this loop is matching the spacing between the pump pulses. I guess I could just say a quick word about how the storage loop works. So the photons, when they come in, are horizontally polarized. They pass through this polarizing beam splitter. If I did nothing to them, then they would simply leave after one pass through the loop. But what I can do instead is fire this Pockle cell that's basically like a wave plate, a voltage controlled wave plate. So you put a couple thousand volts on this crystal and it rotates the polarization from horizontal to vertical. And now that vertical polarization will continually be reflected when it gets to this beam splitter until I fire the Pockle cell again. I make the photons horizontally polarized and then they get switched out. So one of the key things that makes this whole thing work is that the loss, the per cycle loss in this loop is extremely low. It's only about 1.2%, and that's almost entirely dominated by the Pockle cell and the polarizing beam splitter. The mirrors have reflectivities of maybe 99.99%. In any event, the fact that we have less than a 2% loss means that we can integrate, we can look up to about 40 loops. And that's gonna, as we'll see, really improve the performance of the system. So this is a slightly more detailed schematic of the whole thing. So I produce my photons, I put the shorter wavelength photon, the heralding one, into this array of detectors. That's gonna allow me to occasionally detect if there's more than one photon because it won't likely go to the same detector. And then the other key thing in this is I have this fiber delay here. And the reason I have this fiber delay has to do with this fact that photons that are stored in this cavity for longer numbers of cycles are going to experience the loss more. And I'd rather not do that. I'd rather only store the latest one. So by having a 500 nanosecond buffer here, I can basically detect 40 time bins, what's going on with 40 time bins at these detectors. I can figure out which was the last time bin that had a photon pair. All 40 time bins are stored in this fiber delay, but then I know from these detectors, I know which was the latest one that had a photon, and I'm only going to store the latest one inside this storage cavity. So then it experiences the loss less, and that's what we want. And then the output comes here, and I can detect it, for example, on a beam splitter with 2 detectors, and this allows me to characterize how many photons do I really have. This is what you do to try and measure this G2 parameter that I talked about. Because if I only have one photon coming out, then only one of these 2 detectors will fire. But if occasionally I have 2 photons that are emitted, then I would occasionally get both the detectors firing. Okay. So this is looking at the probability that we detected a photon with our heralding detector somewhere within n time slots, and as a function of how hard we're driving. So mu was the average number of photon pairs per pulse. So we noticed that if I drive very weakly, then the probability is basically increasing linearly. That makes perfect sense because if I have a small probability of producing a pair per pulse, and I have 40 pulses, I'm going to have roughly 40 times that likelihood. But if I drive harder, of course, I can't continually to just multiply linearly because things have to saturate at 1. And in fact, we get up to something like a 98% probability that somewhere within those 40 cycles, I've produced at least one pair. So that's extremely good. These are tears of joy coming out of my fellow here. And again, this is to be compared with the fact that normally without multiplexing, 25% would be the highest likelihood that you'd ever be able to have heralding a single photon. Okay, but that was detecting the heralding photon. I still have to store its partner photon in this memory for up to 40 cycles. And of course, there is loss associated with that. So my actual single photon probability at the end is not going to be this 98%. So
Hey,
this is, yes.
I'm just trying to understand the word multiplexing in this sense. Can you just sort of explain what you're multiplexing here?
Yes, so what I'm doing, let me just go back to, I don't know, to this. Instead of having to treat each time bin separately, I'm multiplexing a whole bunch of time bins, up to 40 time bins, and I'm calling that one big multiplexing cycle. So at the end of it, I'm only going to get out one photon pair once every 40 time bins. So I've definitely potentially hurt the overall rep rate, but I've been able to make sure that I know precisely when it's going to come out. It's not going to come out at random in one of those 40. It's going to always come out in always the same time bin, always the last time bin of those 40. So I've traded this temporal space, sorry, bad choice of words, this temporal resource of using 40 time bins, but that's enabled me to push up the efficiency. And we'll see that that ends up being a big win for many types of applications.
And so then, unlike this other thing you were showing us before, you've got one crystal doing this work for you, right?
Correct.
And this multiplexing is something that's, as you said there, excuse me, it's a time multiplexing, and you're drawing all those 40 bins into the same operational bin.
Absolutely.
Yeah. Okay. All right. Good. Thanks.
Yes, and I've really done that, as you say, by using a bunch of time bins and one crystal, as opposed to the previous one I showed, which used one time bin but multiple crystals. And of course, you could also imagine hybrids where you do a little of each.
Okay. Thanks. Thanks a lot.
So Paul, a really question. So if I look at the long time, so if I look at 1 day, how many single photons you can get, that total number of single photons is fixed, right? Given a fixed pump power, no matter whether you do a multiplexing or not.
True. Yep.
Okay. I see. Okay.
Okay, so this is the actual output in terms of the single photon probability, again, for these different sort of pumping powers. And the main thing just to focus on is that we're up now at something like 67%, and that's a photon in a single mode fiber. And so that is, as far as I know, still the world's best single photon source, the one with the highest single photon probability.
So what's causing this to be less than the number you had on the previous slide?
The fact that there is that 1.2% loss in the storage loop.
Oh, okay, good, thanks.
Okay, so another thing that you care is not just that you have a single photon, but you want to be able to use it for something. And being able to use it in many cases for multi-photon experiments means that it will interfere with other photons. And in order for that to be the case, it has to be indistinguishable from other photons. And the way that we can characterize that, this indistinguishability, is we do this experiment called a Hongo-Mandel after the original people who did the first experiment in Leonard Mandel's group a long time ago, interference. So that's where I take the two photons and I mix them on a beam splitter, let's just say a 50-50 beam splitter, and I ask, what happens to the photons? Where do they come out? So if the photons are distinguishable from each other, if one was red and one was blue, then they would act completely independently, and either photon would have an equal likelihood to either be transmitted or reflected. And so I would get cases where both photons were transmitted, cases where both were reflected. Both of those cases would get a photon to the top and a photon to the bottom. And then I'd also get the case where, say, the top photon was transmitted and the bottom was reflected, or vice versa. Okay, that's if they're distinguishable. If they're indistinguishable, I still have those same four processes. But if I look at the two processes that lead to a potential coincidence count between these two detectors, process where either both photons are transmitted or both photons are reflected. If I look at those two processes, and you take into account the fact that there has to be a relative 90-degree phase shift on reflection relative to transmission, that has to be the case for any unitary allowed beam splitter. It turns out that these two processes, assuming this is a 50-50 beam splitter, capital T equals capital R, and I end up with basically 1 over the square root of 2 squared times I over the square root of 2 squared. And the fact that I get that I squared means that these two processes will cancel. So that means I will, in fact, get a complete suppression of getting a coincidence at these two detectors. And that's called the Hongo-Mandel dip. Why dip? This is as I change the relative delay coming into the beam splitter. So if I have the beam splitters arriving at different times, they're distinguishable. These processes won't interfere and I won't get a dip. But when they arrive at exactly the same time, and assuming the photons are otherwise indistinguishable, then that coincidence rate should go to 0. And so that tells you that's a metric that we use in our field to determine and characterize how indistinguishable the photons are.
And what about if they're shifted in phase by a half a wavelength?
It is not phase dependent at all.
Okay.
And in fact, you could kind of just very quickly, you could see why that's the case. Let's say I put a random phase on e to the I phi on this top arm here. I'm going to have that same e to the I phi there, and it's just going to cancel. So this is not a phase dependent effect.
Okay.
Okay, so one reason why it's important for us to test this is you might worry that when we go through, let me go back one more time, you might worry, for example, that when I'm going through this memory, that something is happening to the photons. For example, if there's dispersion, if there's a lot of dispersion and the pulses are getting broader and broader each time, it might be that the photons that have only been stored for 2 cycles would look quite different than the photons that were stored for 38 cycles. And therefore, if the wave packets look different, they're not going to be able to interfere. So it's really important to verify that the storage system itself, although it's enhancing the single photon probability, you don't want it killing the indistinguishability of the photons. Okay, so this is just showing interference of photons from our time multiplex source with a non-multiplexed source, so just a single crystal, and basically showing that we get these Hongo-Mandel dips, quite good dips with roughly 92% visibility, and that's equivalent to the purity of these quantum mechanical, of these photons. Okay, so let's do a comparison with these other sources. So the top line is this other John Wei Pan group source where they did their boson sampling with 12 photons. The next one is this quantum dot source, and then the third line is our source. And even though they are running at much higher rep rates, and I'll come back to our rep rate in a little bit, their overall efficiency is quite a bit lower. So we're quite a bit higher on that regard. This is, again, efficiency, single photon probability into a single mode fiber. The indistinguishability is more or less comparable. But then there's this G2 category, and you will notice that in that regard, we're not doing so well. Remember, we'd like this to be as close to 0 as possible. And the reason that we're not doing so well is that we're pumping hard enough that occasionally we're producing 2 pairs. And remember, I said we're kind of trying to detect the fact that we have those 2 pairs by sending them into this array and hoping that maybe one photon goes to one detector and another photon goes to another detector, and I can see that that's happened, and then I just won't try to store that. But in reality, the detectors we have are pretty inefficient, and only having 4 detectors is not really enough. So we don't really resolve those multi-photon events very well, which is why we have this high value of G2. So what we're trying to do now is install some much higher efficiency superconducting nanowire detectors, which we think we should be able to get something like 95% efficiency at the wavelength that we're talking about. And we've also seen some indications that they, in fact, have some intrinsic capability of detecting the number of photons that are hitting them, photon number resolution. Okay, so assuming that we can get those, unfortunately, our manufacturer, Quantum Opus, they do their fabrication runs at a local clean room at a local university, and they haven't had access to it because of the COVID-19 crisis. So we're still sort of waiting on them. But assuming that we can get that, it should be possible to, with fairly realistic improvements, slightly improve our single photon probability, but really quite significantly reduce our G2. So this is just a comparison of, let's say you didn't want to make just 1 photon, but let's say you wanted a string of, say, 2 photons or 10 photons or 20 photons. because that's the sort of thing you would need for doing these other types of applications. And so this is just a comparison of, for example, this 12-photon experiment that was already done, where they had to wait basically for 100 seconds to get one 12-photon event, or the quantum dot case, where to get 14 photons, they had to wait about a second, compared with our current source, or compared with what kind of source we hope that we're going to have pretty soon. So, for example, with our current source, we should be able to get something like a 30-photon string about once a second. Okay, so that's definitely, and with an improved source, maybe even be able to go out to as many as 50 photons. Okay, so that's all sounding pretty good. What might we want to do that for? So I keep mentioning boson sampling, and let me just put this to rest, as that's probably not a good application. So when we first started this research several years ago, people told us that if we had 20 or 30 photons for this sort of experiment, a successful boson sampling experiment would demonstrate quantum supremacy. So basically demonstrate that a quantum processor could do something that a classical processor couldn't. And over time, that required number of photons has been increasing monotonically. And so many people now think that you maybe need at least 50 photons. And more recently, we've even had people saying you need something like 50 to 100 photons. And basically, even if we're completely tweaked up, maybe we'll get like one 50-photon event a second. But in order to get enough statistics, in order to really do something useful, basically, I don't think we'd be able to do it. And we're certainly never going to get to 100. So I think boson sampling is just not a good application for these sort of sources anymore. Okay.
Paul,
yep.
You were telling us about guaranteed single-photon sources here, right? And you're kind of, yeah. So what's this 50-photon thing? I'm not quite sure I understand where that.
Yeah. So the thing is that if you can make 50 photons, if every pulse that you make, every output pulse has a single photon in it with a high likelihood, then you can get large strings. So you could get a string of 50 pulses in a row, each of which has one photon.
Okay, all right.
And the likelihood of that is just going to be whatever our efficiency is, let's say 0.7, 70% to the 50th power.
Yeah. And so.
And it turns out that if you can do these if you can do that at a megahertz, it turns out you'll still get something. Or maybe with 30 photons, it's more likely that you'll get like one 30-photon string a second, every second. And then you would have to put it into one of these other circuits. Does that make sense?
Yeah, I was just turning my mic back off so I didn't interfere. But yeah, thanks for that. That's good.
Yep. Okay, so maybe definitely a more useful application would be trying to make heralded entanglement. So at the moment, we don't have any sources, optical sources that make pairs of entangled pairs on demand. We have these probabilistic sources. And it turns out that the fact that they're probabilistic and that they sometimes make multiple pairs, as I've been talking about, that turns out to really hurt their application for quantum networking. It reduces the rates that you can run at by anywhere from factors of 20 to factors of 500 or 1,000. But it turns out that there are some circuits that you can make where if you have single photons, reliable single photon sources to drive them, as shown here, then you can probabilistically, but in a heralded way, produce entanglement. So for example, in this case, you send in exactly one photon into each of these bottom modes, A1, A2, B1, and B2. And those photons are kind of going to do their own thing at these various beam splitters. But if it happens that you see one photon at one of these D1 detectors and exactly one photon at one of these D2 detectors, and it turns out that will happen 3/16 of the time, if that happens, in that case, then there are photons in A1 prime and in B1 prime. There's an entangled pair in those two states. So 3/16 of the time when you drive this, you'll get a heralded signal that there's an entangled pair there. And with our source, we think we might be able to get something like 17,000 of those events every second. And once you have a heralded source, then in principle, you could store these photons in other memories just as we were doing for a single photon source, and that would enable you to get a deterministic entanglement source. Okay. Okay, I'll do just one more of these other possible applications. Let's say you wanted to make a source that has not 5 sequential photons, but really a pulse that has 5 photons in it. So you want say a 5 photon Fock state. And what we can do then is I'll still have my same sort of storage cavity here, but I'm actually going to put my downconversion crystal inside that storage cavity, and I'll match the length of the storage cavity to the interpulse spacing, which is not how it's drawn here, but pretend that that's the case. And then I'll continually pump this crystal, and I'll basically count how many photons have been produced, how many pairs have been produced by counting with this detector. I'm just going to keep storing all of them, and because I've matched the cavity length to the interpulse spacing, any new photons that are created basically right on top of the previous number of photons that are already there. So I'll simply wait until I get 5 clicks on this detector. I will then know that I have deposited 5 photons into this other cavity, all one right on top of each other. So in this way, I basically have a deterministic photon adder. And what that enables you to do if you want to make these large Fock states, you still have to create 5 pairs, but instead of having them all be created, for example, simultaneously, I just have to create them somewhere within however many pulses I'm using. So for example, if I have n pulses and I'm trying to create a k photon state, I get an enhancement of n choose k. So if I could do that with 100 bins and I try to make a 5 photon Fock state, I actually get an enhancement of about 75 million. So that's obviously interesting and something that we will be trying to setting up next year, basically. And those sort of states can then be useful for different sorts of metrology and other applications. Okay, so one thing that currently limits our rate is how fast we can fire these Pockle cells. It turns out we can only drive them at about 1 megahertz because they require several thousand volts in a very short amount of time, and the driver just can't handle anything more than that. There has been some recent work at making some very fast electro-optic modulators out of Marco Loncar's group at Harvard. But unfortunately, those, they have relatively low loss, only something like half a dB loss. But that corresponds to about an 11.5% loss. And in fact, that's going to, as we'll see in just a second, that's going to be too high. And in fact, the loss getting into and out of their devices is something more like 5 dB. And so that's going to be really an unacceptable loss for this sort of application. We do have some new funding, a project that started about a year ago from the NSF, trying to develop some much higher rate switches and very low loss switches. But we'll have to see in a year or two if we're able to get something like that to function. So what does loss do to this whole endeavor? It turned out it's pretty problematic. So this is just a theoretical plot. If I were to increase the amount of loss per cycle from nothing to 1% to 5% to 10%, we see basically that we very quickly lose the benefit of being able to do this time multiplexing. And in some sense, this is a bit pessimistic then, because it means it's going to be very difficult, for example, to set something like this up on an integrated optic, a photonic integrated circuit, because getting a 1% loss in such a device is extremely challenging. Also, if there's dispersion in the system that I'm using, that's also going to be a problem, because that will mean that the pulses that go through different numbers of cycles will look different to each other. So one of the reasons that our system is working pretty well is that everything's operating in free space. Okay, so I'm going to skip this slide, these quick, and just the other thing I wanted to talk somewhat more briefly about is quantum memories. And it's also going to be using the same sort of multiplexing techniques, temporal multiplexing techniques. So just as in all kind of processors, memories are important for quantum processors inside quantum computers, for example. It turns out they're also very important for setting up quantum networks. In quantum networks, I might have a bunch of entangled pairs sources as shown here. And in order to link them together, I need to take photons from different sources and mix them on a beam splitter. This is exactly the same sort of measurement I already showed, the sort of Hongo-Mandel measurement. I mix them on a beam splitter, and that has the consequence of entangling these two outer photons that have never talked to each other, that have never been in contact with each other. And if you can do that with enough of these chained in a row, that enables you to make one very long link. But it turns out that only helps you if you have memories that are shown here to be able to synchronize these sources so that they definitely will both be producing a photon that will get to the beam splitter at the same time. Okay, so quantum memories are extremely important for a number of different applications. And there are lots of different types of quantum memories. So people use atomic systems or solid state systems. And these other systems, atomic and solid state, one sort of characteristic feature of them is that they tend to be fairly narrow bandwidth. And I'll come back to that at the very end. What I want to talk about right now is the possibility of using an optical, sort of a simpler memory based on the same sort of thing we've been discussing, just an optical delay line. Okay, so here's how such a memory might work. So I have my photon comes in, it's vertically polarized. I use the Pockels cell to switch it to horizontal polarization, and then it'll keep looping around till I switch it again, and then finally it will come out. So I can just stay in this for however many loops I want. For example, I'll maybe want this loop length to match whatever the repetition rate of my laser is. Okay, so there's some advantages. It can store multiple pulses. We'll see later that it's very high bandwidth, but there is going to be a limited storage time associated with this. So let's say that my Pockels cell in this case, or my cycle loss is 3%. Well, okay, I can go, a bunch of cycles, a bunch of intervals here, let's say 20 cycles, and I still have a fair likelihood that I'll get my photon out. So I'm losing a little bit each time I'm staying in the system, but even if I have to stay in 20 times, I still get my photon out, better than 50% of the time. But let's say I didn't want to just stay for 20 cycles. Let's say I wanted to stay, for example, for 537 cycles. Well, in that case, now this 3% loss is really starting to hit me. So 0.97 to the 537 is basically 10 to the minus 7. So basically, I can store my quantum state, but it just doesn't come out. It's lost due to absorption or scattering and some of the optical elements. Okay, so here's this kind of a nice trick that you can do, though, if you can stack various of these memories together. So let's say I have, we may call this a digital quantum memory. So I have one loop that is 12.5 nanoseconds, one storage system that's 125 nanoseconds, and one that's 10 times longer at 1.25 microseconds. And now if I wanted to store for 537 cycles of this 12.5 nanoseconds, instead of going 537 times through this short loop, instead what I'll do is I'll go 5 times through this longest loop, and 3 times through the middle loop, and 7 times through the shortest loop. And assuming that each of these loops, assuming that the loss is all coming in the switches, then I here take 0.97 to the 5th, 0.97 to the 3rd, and 0.97 to the 7th. And now I have a net transmission of about 63%, which I think we'll all agree is a lot better than 10 to the minus 7. Okay, so we've actually implemented this in our laboratory. This is the project that Michelle Victoria has been working on, where we have the short loop is just basically 12.5 feet on the table, because that's how much space it takes to store for 12.5 nanoseconds. And then the photon that comes out of that goes into another Pockels cell. And if we switch that, if we don't switch the polarization, then it loops around and comes into this other loop and makes a bunch of loops for either 125 nanoseconds for the middle system or 1.25 microseconds for the longest system. And the 125 microseconds we get by having 2 spherical mirrors with a hole, and basically the photons kind of rattle around sort of like a Gatling gun pattern. And that enables us to get 125 effective feet in about a meter separation here. And the 1.25 microseconds requires this sort of modified device where I have 1 spherical mirror and 2 flat mirrors. The 2 flat mirrors are canted a little bit with respect to each other. And basically, we end up with a Lissajous pattern that fills the surface of the mirrors. The photon comes in over the top of one of the two mirrors, bounces back and forth in this system for a couple hundred cycles, and then leaves under the bottom of the other one. Okay, so this is just showing, this is data showing if we were to only go through the shortest loop up to 10 cycles, or through the middle loop up to 10 cycles, or through the longest loop up to 10 cycles, and showing the efficiency that we're getting basically per cycle, per loop in each of these. And this is showing data where we store the pulse from anywhere from 1 to 999 cycles. And there's this kind of a scalloped behavior here, because, for example, at this point, we're going 9 times through the short loop and 9 times through the middle loop. And to go one more increment of 12.5 nanosecond, instead, you can just go through the longest loop once. And that turns out to be much more efficient than going 9 times through each of these other loops. Okay, well, we've also had this running through coupling into single mode fiber. So you could ask, well, how good of a system could we get? So we currently have Pockle cells with transmissions of, with losses of a few percent, and the mirror reflectivities are about 99.9. But if instead you get Pockle cells that are at state of the art with maybe only 1% loss, and mirrors with quite a bit higher reflectivities, which is definitely possible at the moment, then in principle you could imagine storing out to something like 100 microseconds in this 10 nanosecond cycles. It turns out if you go to instead of a digital system, you go to something with a lower basis where each memory is 2 times longer than the other one, then you need fewer switches, and so that ends up being a little bit better. And the other possibility is eventually combining this with some matter-based memory, like the type that Elizabeth will talk next time, if you wanted to be able to add this sort of short time resolution storage on top of, say, a millisecond memory storage. Okay, we would like to be able to store qubits, and at the moment that's a problem, because if I take, say, a polarization qubit as represented here, and I send that into my system, what's going to happen is that the horizontal component is going to be not stored, and only the vertical component is going to be stored. So that's not going to work. So instead, what we want to do is convert the polarization qubits into timing qubits, into 2 time bins that are closely spaced with each other. And we can do that like so. We have a transducer that is going to take our polarization qubits. I'm going to send them into a polarizing beam splitter so that the horizontal component is going to be transmitted along the short path, and the vertical component is going to take this long path. So now I have actually an entanglement between the polarization and the time bin, but I can use a Pockle cell to flip the polarization of just the first photon. I'm going to flip it from vertical to horizontal, and then now I've mapped the polarization qubit onto a time bin qubit. And now I can just send that into my memory. And then after I've stored it in my memory, I come back out and I just go back through the transducer in reverse order and convert back into a polarization state. And the way I've done this, what originally came in the short path on the input takes the long path on the output. Turns out that makes the whole thing phase stable. And what that means is that our transducer itself is gonna introduce a sigma x conversion to what the quantum state is. Okay, so we've measured that by doing some process tomography on the quantum memory. And this is basically the sort of picture that we want, showing that we have this sigma 1 process. And we've done that for both our short loop and our middle loop. We're still working on our longest loop, and shown that we get quite high fidelity for this kind of quantum memory. And moreover, the thing that we've measured is the transducer and then the memory and then transducing back. And what we're maybe really most concerned with is, well, what does just the memory itself do? And so we could do a measurement of just the transducer and then transducing back without the memory in place. And basically we get the same sort of plot. And that enables us to then conclude that the memory itself is acting like the identity at something like a 99.8% level. So it seems to be working really quite well as a quantum memory. Okay, just the last thing I want to say here is about the bandwidth. So in our case, because we're pretty much only limited by the bandwidth of the coatings on the mirrors and how well the Pockels cell works, we actually have an incredibly broad bandwidth of 1.5 terahertz and a time bandwidth product that's something like 10 to the 6 or 10 to the 7. And that's several orders of magnitude higher than any of these other type of atomic memories, and could be very useful for being able to store very short optical pulses, for example. Okay, so in conclusion, we've been able to see this quantum memory working and being able to store anywhere from 1 to 999 cycles. I have a very high broad bandwidth in this. We're able to store quantum states with a high fidelity. And I've talked about storing polarization qubits. Of course, we could store time bin qubits because that's what we're actually doing when we're storing the polarization qubit, and we convert it. And we're also looking into being able to store quantum states that are encoded in these other degrees of freedom. And there's this possibility of combining it with some other quantum memory to be able to get very long storage time and also very good depth of the storage. Okay, so this last slide, we don't really need to spend much time on. It's not things that I absolutely know how to solve. So we'd really like some non-cryogenic detectors, unlike the superconducting ones. We'd like a very low loss optical switching network. We'd like a very efficient long-term quantum memory. I already talked about the need for a deterministic entangled pair source, but one that's really high rate would be good. Some quantum non-demolition detector would also be fabulous. But nevertheless, I can make a fairly conservative prediction, which is that multiplexing of various different sorts, temporal multiplexing, spectral and spatial multiplexing, I think will be very important moving forward, at least for these kind of optical implementations of quantum information processing. So I think I will stop and ask you if you have any questions.
Thank you, Paul, for the great talk. Is there any questions from the audience? I maybe have a stupid question. So you said so for the memory, the limiting factor of the loss is from the switch and the mirror. So given the light is propagating in the air, if you increase the storage time, making the cavity longer, will there be any loss due to the scattering in the air? No, nothing.
Well, I mean, there would, at some point there would be, but it would be very, very hard to measure that. I think that's far down. So if you think about it, the world's longest quantum memory would be LIGO, right? Because then, they have evacuated chambers, so they don't have any loss in that case either. You can certainly, if you're willing to just go to longer systems, bigger systems, then we'd be able to get any kind of memory time we would want. It's just that you do have beam diffraction, and then you need to put lenses in to fight that. I think it's not very practical. It'd be much better to have Elizabeth and her quantum memory.
Sure.
So, Paul,
yep.
Can you think of any way to build a switch that's reflective? Because that's kind of the only way to imagine switching substantially more efficiently with like a bunch of nines.
Well, a switch that's reflective. I mean, all the switches I know in some way are based on putting a phase shift on something. And the phase shift means that you're usually going through something. You pick up a phase shift because you're interacting with something. It's true that you can, for example, have photons incident on a cavity, and inside the cavity you could put like you can make a quantum switch where there's a quantum dot inside the cavity, and depending on whether that quantum dot is excited or not will change whether or not the cavity is on resonant with the photon, and then it might just either reflect off. But the thing is, if it doesn't, then it has to go in and interact with the quantum dot, and then you're limited by the finesse of the cavity. So,
but I think you can get, finesse of the cavity, that's going to be many nines compared to.
Yeah, but I'm saying that's going to slow it down then.
I see.
Right, the fact that the finesse is really high means that effectively you could think about unfolding the cavity, so then it looks really long, so then it's not very fast.
Yeah, I wonder if you could use a cavity that you're, rather than having a quantum emitter in it, basically heating it with another laser.
Yeah, so you could think about that as a Yeah, but I guess my point is, as soon as you do the cavity, then you still have, in order to know that, in order to measure that finesse, in order for it to be high finesse, it means you've had to interact with it for a long time. So in some sense, one of these other switches that we are looking at is an optical one, where you have an optical fiber in a Sagnac interferometer, and you put a bright optical pulse down, and that, through the Kerr effect, puts a pi phase shift on, and it switches where the photon comes out at the end. And that's been demonstrated to be, sub picosecond. So it's quite fast. And then the question is just how low can you get the loss in this optical fiber? And it doesn't need to be very long. It only needs to be like a meter long. So people have seen like a 90% transmission thus far, but I think a lot of that is also in-coupling losses. So we could probably push that up to maybe 98%, something like that.
Yeah, okay, thanks.
Hey, Paul, I
Yep.
was intrigued by the plan to make, say, an n=5 Fock state with that cavity with the nonlinear crystal inside the cavity itself. So it seems like when you do your process, or you shoot in a pump photon, you generate these two daughter photons.
Yep.
That is being sort of driven by quantum fluctuations in that one first event. But then the second event, where you have one of your stored daughter photons coming back, passing through the nonlinear crystal at exactly the same time that the pump comes there, now you've got an actual signal to drive the emission of light. And it seems like the photon statistics might be interesting to think about there in
Absolutely.
the nature of the state, I guess.
Yeah, absolutely. That's a very good catch on that. That's absolutely the case. So the more photons you have in here, the more likely you are to simulate the production of another photon. So in fact, if you really want to get to 5 photons efficiently, the way that you do it is you start driving a little bit harder. And let's say that this upper left, upper right detector is a photon number resolving detector. And you try to, for example, first make 2 pairs or even 3 pairs. And then you turn down your pump power so that you don't overshoot. But it's absolutely true that what you have here is a photon adder. And so you could have any kind of a quantum state going in here. It wouldn't have to be vacuum to start with. And you can even run this in reverse. Let's see if I have one hidden slide. Maybe I have one hidden slide. Yes, I do have one hidden slide. If I can just unhide it. Are you able to see that right now, that slide?
I can see that, yes.
Yeah, so you can do the same thing with a photon subtractor, where you just have a very weak beam splitter, and you can send any state in at all that you want, a coherent state, a squeeze state, a Fock state, any kind of state at all, and you can let it very weakly interact with this beam splitter. And then once you get a click at this detector, you know that you subtracted a photon from it. And so you can get extremely interesting and in some cases pretty useful states for quantum metrology, for example, by doing these photon additions and photon subtractions.
If you did have like 3 photons in your stored state, and then your pump pulse came in, and then you had this stimulated process to generate more photons, would that make that state unusable for you then? Or is it still, is a Fock state, and it's going to be fine, even though it came about from a stimulated process as opposed to spontaneous?
Yeah, it doesn't know. A Fock state is a Fock state.
Yeah, okay. All right. Yeah. Well, anyway, very interesting.
Okay, another question from Marius. Can I combine my memory with other quantum devices' ion traps? Yes and no. So the memory itself, in principle, would be fine. Although, for example, the photons that come from an ion trap tend to be pretty narrow bandwidth. So they tend to be pretty long. So let's say that they were 100, let's say it's 10 megahertz bandwidth. Those are photons that are then going to be 100 feet long, which means that in order to trap it in one of these cavities, that means that my cavity has to be at least 100 feet long in order to completely have the whole photon wave packet in. So that's not so good. But there are these techniques that people have started investigating where you can convert you can either expand or compress a pulse, an optical pulse, using so-called time lensing. And people have been able to now generate bandwidth compression of up to a factor of 1,000 with that. And so then it might be possible to have basically a transducer that enables these different systems to talk to each other.
Well, thank you.
Any other questions? I've kept you
Okay.
over.
All right, any more questions? Well, if not, let's thank Paul again. Thanks for the great talk.
Thank you, everyone. I'm looking forward to hearing Elizabeth's talk next week. No pressure, Elizabeth.